Okay, today we're going to look at more composites with equations. And so this is going to be the first example. Now, you have heard me say over and over and over again, when you have a number, you start on the inside. Do I have a number right here to start with? Then guess where I'm going to start? On the outside. I'm going to start by writing down the function called f of x. But instead of writing down the x, what am I writing? You see the parentheses? Instead of writing down the x, I wrote down the parentheses. Because in place of x, I am going to substitute g of x. I'm going to take this function called g of x, and I'm not going to substitute a number, I'm going to substitute the whole function. I should say expression. In place of x, I substituted all of this, that was g of x. And then, how do you do that? This needs to be squared. And so that's not 3x squared or 9x squared plus 16. That's not how you square a binomial. So I'm going to go up here in this little corner where I have some space, and I am going to square this by multiplying 3x plus 4 times another 3x plus 4. That's what squared means. You multiply it by itself. And that would be 9x squared. 3 times 4 would be 12x. And a 12x and a 16. And then you would combine the 12 plus another 12. So when you square this part right here, you get 9x squared plus 24x plus 16. And then I need to distribute the negative 2. And then down here at the end, I have a negative 3. And then I need to combine like terms. So this would be 9x squared. This one and this one are like terms. 24 minus 6. And then this one and this one and this one are like terms. 16 subtract 8, subtract 3. I am not going to be able to get a final number. This is going to have an answer that is an expression. And how did I get this expression? By substituting one function into another function. But would I get the same answer if I substituted it the other way around? When you have a number right here, you start on the inside with the f of x. If I don't have a number, then I am going to have to start on the outside with the g of x. And that's this one up here. 3x plus 4, 3x plus 4, and in place of the x, I put a parentheses because I am going to substitute f of x. Over here, I'm going to substitute the x squared minus 2x minus 3 because that's the function f of x. And then three x squared minus 6x minus 9 plus 4. You do know that you stop distributing when you get to the end of the parentheses, right? Combine like terms. These are the like terms. When you combine those like terms, you would get a negative 5. Again, this doesn't reduce all the way down to a single number. You have the composite function. Example number 3, h of g of x. When you don't have a number here to start with, you start with the outside function. And that is x minus 2. In place of the x, I put a parentheses because I am going to substitute the function g of x into the parentheses. G of x was 3x plus 4. And now all you have to do is combine 3x plus 4 minus 2, and so that would give me a plus 2. Is that too hard? Not really hard? Well, let's step it up a level. What does it mean to do the composite with 3 functions? If you do not have a number to substitute, then you are going to start on the outside. G of x was 3x plus 4. And I'm going to substitute h of x. The next one in the line. And so h of x was x minus 2. G of h of x, 3x minus 6 plus 4 would be 3x minus 2. Have one more substitution. 3 times x minus 2. But instead of the x, I put the parentheses because now I'm going to make another substitution. F of x, at the top of your page, x squared minus 2x minus 3. distribute three times x, 3 times 2, 3 times 3, and then the minus 2. So when I have done all of the substitutions, 3x squared minus 6x minus 11. So, you think you can do that? But are you wondering why would you want to? So let me give you an example of a kind of problem that it might be useful to be able to do composite functions. So, in this example, I suppose you don't want to write the whole word problem down, so we'll just write down the key parts. The new car dealership is discounting all new cars by 12%. At the same time, the manufacturer is offering a $1,500 rebate on all new cars. And so the new car that I want to buy is priced at $24,500. So I want to buy a new car, $24,500. The dealership that is selling the car is discounting the car by 12%. And the manufacturer, Ford, Chevy, Toyota, wherever I'm buying the car, is giving a rebate of $1,500. So, does it make any difference whether you take the 12% off or the $1,500 off first? Or would it be the same either way? Well, let's find out using equations. We're going to let x equal the price of the car. And then d of x would represent the equation for the discount price. And r of x would represent the rebate price. Now, we're going to set up the equations to figure this out. It can be figured out without equations, but we're going to set up the equations. And when you are using equations, you cannot use a percent into an equation. Whenever you have a percent, you have to change it to a decimal before you can put it into an equation. The meaning of percent is part out of 100. And 12 divided by 100 would be 0.12. And some people have a little bit of difficulty figuring out how the discount works. The discount is 12%. How do you figure out how much I'm going to pay? Do I multiply the 0.12 times the price of the car? Not exactly. And then you have to subtract, if you multiply the 12 or the 0.12 times the price of the car, that's how much you get taken off. But I want to know how much I'm going to pay. So you have to take the price of the car and subtract the discount from it. Now, this would be 1x, and that's like terms, so when you subtract that, that would be 0.88x. If you take 12% off, then I'm going to have to pay 88%. Okay, what about the rebate's easier because you just subtract a rebate because it's a straight dollar amount. So, we're going to use a composite to figure out which way it's better for me, the consumer, to purchase the car. So this would mean that I'm going to start with the discount. I'm going to start with the 0.88, and in place of the x, I'm going to substitute. Now, I could distribute that, but distributing a decimal, that's going to be ugly, so I'm just going to leave it like that. Or would it be better to do it this way? Start with the rebate and substitute in the 0.88x. Well, it's a little bit hard to tell from there, so let's get out our calculator, and I'm going to be using my Desmos calculator and figure this out. So the first equation was y equals 0.88 x minus 15. Why is it not? I'm telling it to type. Why isn't it obeying me? Y equals 0.88. There we go. 0.88 x minus 1500. Okay, did I get the decimal in the right place? Did I type the first equation correctly? My second equation was minus 1500. Are those my two equations? Did I get them typed in there right? Okay, so now I want to figure it out for the price of the actual car that I was going to purchase. Anybody want to guess which one's going to come out better? 24500. Did I type it correctly? $24500. Does it make a difference? Not a whole lot, but it did make a little bit of difference. So for the first one, I came out with 20,240. For the second one, I came out with 20,060. So it is better to apply the discount first and then the rebate. Do the 0.88, the discount first, and then take off the rebate. And that gave me a little bit cheaper price. Now, did I have to use equations to set this up? No. But the reason you would set it up with equations is if I worked at the dealership and had to figure this out over and over and over for different priced cars, once I get the equations set up, it's real easy just to change. Maybe I decided I wanted to buy a really nice car, $50,000 car, Cadillac. I just change the price of the car. I don't have to go refigure out the equations. And so if I was like working at the dealership and I had to figure this out over and over again, I could set up equations one time and then just plug in the car number, and I wouldn't have to repeat the same calculations over and over again. So this is one example of where you can use composites.